Hello and welcome to another episode of Building Better Systems. My name is Shpat Morena.
And I'm Joey Dodds.
Joey and I work at Gawa. Gawa is a computer science R&D lab focused on hard problems, trust, cybersecurity, and a lot of other fun stuff.
Today we're joined by Nikhil Swamy, who is Senior Principal Researcher in the RISE group at Microsoft Research. This is kind of an exciting one for me because back when I was in grad school, Nick came and visited, and it was really inspiring to see somebody doing industrial research like Nick was. So very excited to be talking with him today and to hear a bit about what he's been working on. In particular, we're going to talk about a bit about his background, and then we're going to discuss a language that he's co-created and continually developed called F-star. F-star is a dependently typed language that you can use to both program and prove things about the programs that you write. We'll talk about what makes that language special and unique from other similar languages, as well as some of the applications of F-star. Let's dive in.
Designing, manufacturing, installing, and maintaining the high-speed electronic computer, the largest and most complex computers ever built.
Thanks for joining us, Nick.
Yeah, it's great to be here. Thanks for having me.
So before we dive into what you're working on now, I'd love to hear a little bit about your background and how you got interested in the field of programming languages.
That's a good question. So my background broadly is I grew up in India, and I came to the U.S. as an undergrad, and I went to a school called Hampshire College in Massachusetts, which is kind of a liberal arts school. No grades, make your own major kind of place. It was a lot of fun. And the school is very kind of oriented towards, self-directed study in some sense. And I found a couple of great professors there who were interested in, who got me interested in computing and physics and math and things like this. And I worked with them on, this was like in the late 90s, I was working with them on quantum computing and applying sort of search algorithms to find better than classical quantum programs, and then trying to prove that the programs that we actually found were correct and solved whatever problem we were trying to solve. Like, that if it's a circuit to solve something, that it was actually solving it with some, finding the right answer with some correct probability, this kind of stuff. So that's when I kind of really got into, or understood that, hey, it's actually interesting to try to prove stuff about programs. And I learned a bunch at that time about, automated theorem proving techniques. And well, actually, I thought I learned a bunch, but I learned surprisingly little. And, then learned that, wow, I actually hadn't learned, like, there's so much more. And I went to grad school at Maryland and thinking about, like, well, initially thinking about, like, hey, I might try to do some things like in the AI space. But I then kind of had some sort of moment, I guess, in grad schools, as that you do sometimes, where I realized that, like, hey, being able to prove properties about programs was a really like powerful idea for me. And I worked with Mike Hicks, my advisor at the University of Maryland, on a programming language called Cyclone. Cyclone is it's like a C-like programming language with a type system geared towards proving memory safety, and with ideas in Cyclone that were maybe somewhat a bit ahead of its time in some sense. Things like linear types and being able to use sort of custom memory management strategies, everything from unique pointers to reference counting to even in some cases, conservative GC. Lots of ideas from Cyclone, sort of in region-based memory management and so on. So I think, now maybe find a home in languages like Rust. And I learned a lot at that time from Mike and the other people working on Cyclone about programming languages and type systems and being able to prove things about programs before you run them. And that's how I got into this stuff. And then for my thesis, I was more, building on what I'd learned in Cyclone. I started to explore some ideas in dependent types and see how, can you add, just a little bit of dependent types to a programming language and get it to prove properties that, I was at the time interested in security properties. I still am. How can you get away with adding just a little bit of dependent types and be able to prove, I don't know, things like the correctness of access control enforcement or information flow control policies, things like this.
And if we don't have anyone that's familiar, could you give us a super quick glimpse? Because I think it's going to come up again in this conversation. What is a dependent type?
Right. So all right. It's a kind of a profound question in some ways.
Yeah.
But in a simple sense, it's it's a way to kind of encode a logic in the type system of a programming language. And the word dependent, maybe it's a little bit scary, but it's actually a really simple thing. It's like you can have a function whose, usually a function, if you give it a type signature, it's a function that takes an integer and returns an integer, let's say. That's it's like a simple type for a function. But you can have functions that are, whose return type can depend on the argument. And it can do things like, if you call it with the integer 17, then it returns, a vector whose length is 17. Or you could even be things like, hey, you call it with a Boolean, and if you call it with true, it returns a string, and if you call it with false, it returns, an integer, let's say. So that's where the word, I think, dependent comes from. But this mechanism, which you can kind of think of as like the way the examples I gave you are very kind of programming centric, but this basic mechanism allows you in a very kind of foundational way to encode within the type system, very powerful logics that let you, build, all of mathematics in some sense inside this logic, which doubles as a programming language. Now, dependent types, because of this very powerful thing, you don't see them that often in mainstream programming languages. You're beginning to, but they, the kind of languages that me and my colleagues work on, I'm sure we'll get into more of them, but they're fairly, I don't know, they're pretty fancy. I mean, to put it bluntly. So I was trying in my thesis work to sort of see, well, I don't want full dependent types. What can I, can I just inject just a tiny bit of dependent types into my language, and, how much mileage can I extract from that? Like, what kinds of things can I prove if I get, dependent types light? And then I guess it's, I don't know, 10, 15 years later, I'm no longer doing dependent types light. It's kind of, it's like the
heavy dependent types.
Yeah, the entry, the gateway drug or something. You start doing it a little bit, and then after a while you're fully in bed with dependent types, and it's all
fully in bed with dependent types. I think we got our title for the podcast.
Cool. And so now you're at Microsoft Research and have been for a while, and you've been working on increasingly more dependent types, I guess, in a language called F-star.
That's right. Yeah. I've been at Microsoft Research since about 2008, and I worked there at a group called RISE, Research in Software Engineering, and I work on F-star, but broadly on programming language techniques, programming language and program verification techniques to to prove programs correct, to prove them secure, to prove things like resource bounds and about them, things like this, proving things about programs
through program language design.
Yeah, through programming language design, where in these new programming languages, to sort of the languages facilitate writing programs and their proofs together, is to make it possible and maybe easier to actually write programs that are correct.
A lot of this work from where you started to the work at Microsoft sounds like part of it has maybe culminated is the wrong word, but it has led to this language that you're working on, which is F star. Wonder if it would be a good place to start for you to tell us a little bit about it.
Yeah, sure. So F star is this programming language. It looks like superficially, it looks like many other functional programming languages. Things like languages in the ML family, things like OCaml or F sharp or even Haskell to a certain extent. So, which is to say that it's a mostly functional, statically typed language. And where what's maybe unique about it is that it's it has I'd say like three maybe unique features. The first is that it's dependently typed, meaning that the type system is more powerful than these other languages that I've mentioned so far, things like OCaml or F sharp and so on. It has a type system that is, it's got full dependent types similar to other languages that you may have heard of, things like Lean or Coq or Agda, or, other dependently typed languages. But it is different from the dependent types that you see in these other languages in that F star is based on an extensional type theory, which is slightly technically, we can talk about that at some point if you want. Different than the type theories that are implemented by these other languages that I mentioned. I think this extensionality thing is kind of important because it enables, making F star sort of a programming first kind of language rather than a language in which you say maybe some of these other languages, they're kind of set up as proof assistants in which you can do sort of mathematics at a very deep and abstract level. F star is more kind of programmer centric, where you wouldn't necessarily fire up an F star session to formalize category theory or something. I mean, you can if you want, but that's not what people use it for. It's more like you use it to write for building programs that you want to execute. And this in doing that, like as you're writing programs and you're writing sort of software, it turns out, as probably you're both aware, like when you're writing a piece of software, there are typically, and you want to prove it correct, there's maybe a handful of interesting theorems that you want to prove, but the bulk of the things that you're trying to prove are really, really tedious, low level, tons of, you're mired in details, hundreds, thousands of small proofs that help towards maybe you have some interesting insight about a big invariant, and there's a handful of big proofs. So one thing that F star really aims to do is to try to reduce the human overhead of having to write these thousands of small proofs all over the place. And the way that it does this is by using, and this is kind of the one of the unique things about F star, is by using an SMT solver. An SMT solver is an automated theorem prover that if you feed it a problem in some logic, and it's usually some things like first order logic plus some reasoning capabilities about arithmetic, things like this. You feed it to the SMT solver, and the SMT solver can try to decide whether a particular formula is valid or not. So what F star does is that it analyzes your program in its dependently typed logic, produces these a large number of proof obligations that pop up when you're trying to verify even 10 lines of code, and feeds that to this SMT solver, which tries to do the proof for you. Now, I mentioned at the beginning that extensionality was really important here, and one of the reasons is that the particular flavor of type theory that F-star uses is designed in a way to enable this kind of, dispatching proofs to an external theorem prover that can, implicitly prove many properties about your program while you're writing them. So that's kind of, so dependent types and SMT solving, that's kind of two important things about F-star. The third thing is that, when I want, me and others want to write software in F-star that is efficient and, can be low-level software that's doing, things like efficient network communication or cryptography or, things like this. So this kind of software is in many ways inherently effectful or imperative in a sense. Although I said at the beginning that F-star is sort of a mostly functional language, the way in which we use F-star is by encoding within the functional language other sub-languages that allow you to reason about computational effects. Things that your mutable state or raising exceptions or doing I/O, things like this. You can reason about that. You can write programs that do these things in F-star and reason about them within F-star. And so F-star has this effect system, and that's the other unique thing about F-star, that it's dependent types, SMT solving, and effects. And that package together is we use it to build a variety of things in the kind of domains that I've mentioned. Like a focus for us recently has been low-level secure communication software. That's ranging from things like cryptographic protocols to say a network packet parsing, things like this that we implement in F-star, prove correct, and then execute as you can get out of F-star. You can get C code or assembly code or whatever, depending on which of these fragments of F-star you program, and you get out this imperative low-level software that you can then deploy and run.
So it's in somewhat active use for real things, it sounds like. And then if that's somewhat correct.
Well, I'd say there's a small community of active users,
okay,
who are me and my colleagues at MSR, several of us use F-star to do things with it. Like, something that we've done recently is, there's an F-star sub-language for specifically that's for writing low-level parsers correctly, parsers of things like network message formats. So we have a verified parser generator that we've implemented inside F-star, and we use this. Is
this EverParse?
This is called EverParse. That's right. Yeah. So we use this to build the network packet formats used in various parts of the Windows kernel, and we extract high performance C code for parsing those packets, and for the last maybe 18 months or so, we've had our verified parsers produced by F-star, running inside Hyper-V, inside the Windows kernel, in several releases of Windows so far. Yeah. So there are pockets of such people who even outside MSR, there's some people who use F-star to deploy verified cryptography in the Linux kernel or in Firefox, and so there's
yes. Well, so I have a couple questions about that, that's awesome. You at a higher level than just F-star. So first of all, when we're talking about dependent types, you said they don't end up in programming languages that are more generic or more used because they're a little complicated, is my simplified version of what you said. Yeah. But it sounds like you've made this language suitable for programming, in the large, and yet, designed sort of dependent type theory into it. How'd you make that happen? And is it the case that this is more approachable?
I mean, I think there's still a long ways to go. I'd like to think that at least some of what we do in F-star makes dependent types more approachable to certain kinds of people. It's still, like I said, a very small community of people who are using this stuff. But I think I'm optimistic. I think we're on a trajectory where as we see more successes across the several dependently typed languages that we have out there today, and as you see, students coming out of universities around the world, gaining more experience with this kind of stuff, where you look at, if just from a personal experience, like if I think about the interns that I had when I joined MSR in 2008, super smart students, but at the time, programming like this in a dependently typed language was like the bleeding edge. Like not everybody had experience with it, but today the interns that you get, like everyone has done. Many of them have done some part of Software Foundations, or they've programmed in Coq or Agda or something, and it's not. It doesn't feel alien to people, many people anymore. It's just like, okay, I can just hack my way through this proof, no problem. And so I think that the community of people who have a certain kind of baseline skill to approach these things that were previously quite esoteric is that community is growing, I think, quite fast. So I hope that in a few years, like languages like F-star or Lean or so many others will no longer be as esoteric. Yeah,
it's a great word for it.
Well, it's a really important perspective, because sometimes when we look at these things today, it's a small community, right? By most metrics of programming language communities. There is kind of hope, because if you look 10 years ago, dependent type was it was kind of felt new, and now it's now you have a talent pool to draw from, and there's no reason that growth should slow down. So that is a really important perspective to say, it's not huge yet, but we've made progress. Things like F-star and Coq, and I think Lean is bringing a whole new group of people sort of into the dependent type sort of world, and it's really exciting to see that growth, and definitely important to acknowledge all the progress that's been made in the last 10-15 years.
Right. Yeah. I think that maybe the answer to me, one way in which I see sort of more growth happening is and maybe as a kind of as a functional programmer, this is not that surprising, but I really see like the domain-specific languages is a big part of the answer. That you have these frameworks that are super powerful. You can formalize all of mathematics in them if you want, but most people don't want to formalize all of mathematics. They want to do some very specific thing. Like I don't know, writing in our case, for instance, taking ever parse again was, I'm not going to unleash the full power of dependent types for someone who just wants to write a packet parser. I'll design some framework within my, some language within my very powerful framework that's tailored towards this very specific usage, where you kind of that sort of reins in the complexity and makes allows a person to get value from it without having to understand all of it.
I'm laughing a little because you sort of mentioned that, and I think Leo had this experience where maybe he thought the same, but then the entire math world sort of showed up at his door and said, "We want to formalize all of mathematics with dependent types."
No, that's true. That's true. But fair enough. Yes.
But certainly not everybody wants to do that, and the uses seem to be fairly different. So yeah, I mean, I guess on a related question, since we're mentioning Lean, and I think maybe this gets back to the extensional intentional kind of thing. But we did talk to Leo a while back, and one of the things I've sort of been wondering about since we talked with him is like Leo obviously understands SMT solvers very well and knows what they can do. From the sounds of it, he started out trying to write something that could make use of SMT solvers and that could let you get more work done before the SMT solvers do their thing. But he ended up in a world where like Lean doesn't speak to SMT solvers very well or at all at the moment. And is that sort of the extensional intentional distinction there, or did something else happen in your opinion to sort of cause him to move away from that?
I think you could make this the SMT thing work inside an intentional type theory in certain ways, and and I think within Lean too, it could. I think it could well happen. I talked to Leo a lot. He's taught me a ton about both SMT solvers and type theories.
He was saying the same. He was saying the same about you.
He's being kind. It's definitely the other way. But I think. I mean, if I was to guess, I mean, I'd say, we may still someday have a SMT solver inside Lean. I think it's just that Lean has really taken off in this math community, where the priorities have been to serve the needs of to meet and serve the needs of that community, and maybe SMT solvers have not made it to the top of the priority list yet, but I expect someday they will. But the kinds of things that and people have built SMT assisted proof automation in other frameworks. From there's some in Isabelle notably, which is not dependent type theory, but SMT solvers work very well there. But also there's some work in Coq doing things like this. But the thing in F-star that makes it different than, say, Lean or Coq or other dependently type languages is that you can use an proofs done by an SMT solver, or proofs done. They can be done by an SMT solver, but they could be done by any other means too, by a tactic or whatever. You can use them to implicitly convert types everywhere. That's the main thing. Like you can if I have a vector of whose length is n plus n, I can implicitly treat it as a vector of length m plus n, because of course m plus n is equal to n plus m, and an SMT solver will tell me that instantly. But in an intentional type theory, if you want to do this simple manipulation of converting these two types from one to the other, there's a lot of, well, Joey, you're smiling because you've probably had to confront this kind of thing before, because it's kind of a mess. I mean, to do these what seem like obvious conversions is a bunch of bureaucracy in an intentional type theory. You have to explicitly have these equality witnessing conversions and things like this, and these things just go away in an extensional type theory, and maybe makes it more amenable for me to just call an SMT solver at this point to just decide if n plus m equals n plus n and just be done with it without having to, mangle my program.
Gotcha. So it's not necessarily impossible in this intentional setting, but it's quite a bit easier, I guess.
Yeah.
In the extensional setting to just take what the solver says and kind of go with it. And not have to do quite so much bookkeeping around why is what the solver says correct? How do I propagate it through my terms and things like that? That makes a lot of sense.
One of the great things about being a podcast host is that when I'm out of my depth or don't understand something, I can move us on. So here it is me moving us on to another topic.
Thank you.
But jokes aside, pseudo jokes aside, I want to see if, so there's probably a lot of people listening who do work on their own languages, or they're doing research and trying a few new things with maybe toy languages that one one day might get a larger user base. I'm wondering if we can talk about how you think, especially since F-Star is getting some use, about how you think about how do you evaluate language design from the lens of, is it useful and will people use it? I wonder if you have thoughts there to share.
Yeah, that's a good question. I mean, I have some thoughts. I don't. My thoughts aren't necessarily, I don't have any sort of deep pearls of wisdom here. But I think one thing I can say is that somehow co-evolving your language design with a problem that you really want to solve is really important, so that you're not just you're not just building something that you can't keep evaluating. You need to be able to evaluate what you're doing, like every day. Is this actually helping somebody solve some problem? That often means pairing up with some domain expert, because sometimes, as a language designer, you can sort of, for many of us, I think the aesthetics of some of lambda calculus and all this can be quite alluring, and you just kind of go off and design something because like it's beautiful or something, and that's fine and it's fun, but I think finding a way to sort of pair up with a domain expert from some other domain who's really trying to solve some problem, whether it's doing math or whether that for instance in the lean community that's been a big driver. I think for F-Star that driver has been a lot about has been cryptography, and people who are interested in or sort of implementers of cryptography, not necessarily cryptographers as such, but people who want to build efficient implementations of crypto protocols or crypto primitives. And so I think finding a way to, and that sort of cycle has been, I think, really helpful for F-Star. We propose some new way of doing proofs, and immediately, our friends at INRIA or CMU will try it and tell us, if it makes sense or not, and we'll iterate. So I think, and this is not by no means is it like a huge user community. It's maybe we're talking, this kind of the close circle of people who repeatedly give us feedback on new language features is something like, maybe 50 people, nothing crazy, right? But even that is enough, I think, to keep you honest in your language.
When we interviewed Alistair Reed, he had this, well, I guess he had a paper called it, but I like the idea as well, as kind of the idea of meeting developers where they are. And that's really, I think that's kind of what DSLs are all about to some extent, is like, we have this language, it can express anything in the world. You can write any program in the world with it and say anything you can express in a logic about it, right? And that's great. And that, that'll get you a POPL paper or maybe an ICFP paper. But that's not enough to, of course, get somebody using it. And the idea they were all about is like, we need to minimize the time between when someone starts using this thing and when they see some sort of good results, basically. And so, DSLs are a way of bringing that time way down and minimizing the things they need to learn, I guess. Have you done areas other than cryptography where you've seen success? Is it possible to layer up different sort of DSLs on top of F-Star?
Yeah. So, one of the things that we're looking at, it's sort of systems programming, but systems programming that you with concurrency and that you can sort of prove correct in a separation logic, which is a way to write imperative programs, concurrent programs in F-Star, and reason about them in this thing called separation logic. Separation logic it's an active area of research in the PL community, in the program verification community, and it's a way to sort of structure proofs that's more modular, if I were to just put it in a nutshell, and are things that we are from a purely sort of language design perspective, we started to look into this seriously, maybe, after our experience trying to do proofs in for crypto protocols and so on in a framework that didn't have separation logic. And we were able to get things done, and we have a large code base that's done without separation logic, and all this code that's deployed in various places doesn't use separation logic. But we noticed that our proofs are way harder and hard to maintain because they lack this kind of modularity. So we've been looking at, so motivated by that sort of, empirical observation that we have this code base, it's kind of many hard-fought victories. How can we make it a little simpler? Maybe by enhancing the logic in which we work. And so that's something we've been looking at recently, and using it to do things like, it's building on what we've done with crypto and also parsers and so on, but it's trying to apply some of these ideas in we have a project where we're trying to use this to do things like high assurance monitoring of cloud services. Like, can you write a monitor for a service that's going to observe the interactions that a client has with that service, and and provide some guarantees about that interaction, cryptographic guarantees about that interaction. Where, for instance, if we notice that the server is responding in a way that's incompatible with the trace of messages that the server has seen so far, then we, except for some small probability of you breaking a cryptographic hash or something, our monitor will notice this and signal an error. Signal that the service has deviated from expected behavior. So things like this. So it's so still there's still some cryptographic components to it, but sort of moving beyond just crypto primitives or protocols.
Yeah, that's sort of one of my favorite uses of formal methods, maybe almost ever, I guess, is like the state machine work you all did with TLS, where you did about the same thing. You made a verified implementation, and maybe it wasn't quite high performance enough, or there were some other demands that it wasn't quite meeting to run in production. But what you all were able to do is know exactly what a perfect TLS conversation looks like, because you made a verified implementation, and then just have a bunch of TLS conversations. And whenever the other side messed up, you said, they messed up. And you all found like a lot of serious TLS implementation bugs in systems that are running in production, which was, I think, a really cool result, and a really great way to make a lot of formal verification sort of directly useful to production systems, basically, even if people weren't kind of ready to use the verified thing yet.
Yeah, that's really cool work. I wish I could take credit for it. It's not actually mine. It's work by my close colleagues and friends at MSR, Cambridge, and INRIA in Paris. It's Antoine Deligna Lavaux, Karthik Bhargava, and Cedric Fournay, and others. But yeah, that's really cool stuff.
They did do the verification in F-star, at least to some extent, right? So you can get second degree credit, I guess. Sure. But this sounds like a similar sort of application where, but it is as nice as it is to deploy verified code directly. The existence of verified code allows you to do a lot of different things, even if people aren't ready to run it right away.
Right. Yeah. Totally. Yeah. Although so yes, I second. I totally. I buy what you're saying, Joey. But I'm kind of also, I think, we can get to a point where, verified code is, it is sort of has no excuses. Like it's it's correct. It's as fast. It's maybe there should be no reason for you to not deploy this in a production setting. I think we're getting there in several sort of. I mean, I think the main barrier is it, is the component that you're trying to verify, is it high value enough? Like, in terms of, is a flaw in that component, severe enough that it warrants the investment of so much human expertise into producing this verified component, producing and then maintaining it. And so there are some places where this makes sense. Like, if there's a bug deep in the virtualization stack that's isolating cloud tenants from each other, then that's a bug that could cost billions, and maybe in those situations it's worth strategically replacing some key component of that virtualization stack with a verified component, and the same goes for cryptography. So there are these I think these sort of select few areas where the economics is beginning to make sense.
The other side of economics, I guess, that people take into account here is if their team isn't the one that developed the code, but they need to maintain it, they need a decent story there. And one of the arguments, I guess, is you're less likely to need to maintain it because we're more likely to have gotten it right. But sometimes that's not sufficient. I'm curious, you all got those parsers deployed, apparently teams, likely teams other than your teams and Microsoft are now sort of responsible for those in some sense. And I'm curious how that's gone and what, what was convincing in terms of you should use this code. You're going to be able to maintain it, or we'll be able to help you maintain it. I don't know how those conversations go.
Right. Yeah, I think the maintenance thing is a big one. And I think this argument that it's verified, so the maintenance cost is lower, it's a bit facetious. I don't really buy it. Like, there's, things change. Sure, the code is verified, but you're going to find that your spec will change because the needs of this component are going to change. And then so maintenance is a big issue. I think in the specific case of the one that you mentioned of us deploying these parsers, the answer again for us was like, it's the DSL thing again. We're not going to, if it's just an arbitrary piece of F-star code that's going to be, someone has to maintain, then this is, if you're not an F-star expert, then that's that, or you don't have an F-star expert on your team, that's a really hard sell. But if what you have is instead you're writing, you write a format description in some C-like syntax, and the proofs happen automatically behind the scenes, then the maintenance story is much easier. The verification tool is just a tool as part of your compiler workflow. You're not interacting with it directly, and so that's a bit of an easier sell. Like people who don't have to be, F-star experts to maintain and evolve this code. We still work closely with the teams that use our code, and if the code has to be evolved, we're usually part of the code review to make sure that it's being done in a reasonable way, things like this. The other context, I think, is also, in cases where the component you're delivering has a very clear spec, like you want to deliver an implementation of SHA or something, and my colleagues who do this, have done this in many situations, often deliver C code that comes out of the toolchain, and the C code is designed to be, we take a lot of pains to make it look pretty and human readable and so on. My colleague Jonathan Protsenko is that he's responsible for a lot of this, like building a tool that emits clean-looking C code from F-star. Yeah, that's maybe another way. You deliver the artifact, and maybe if things are stable enough, like you don't expect the spec to change of this kind of primitive, then the maintenance question becomes easier as well.
Right. But if you deliver reasonable looking C code, the worst case for that team is that you all disappear, no one knows how to maintain it, and they've still got a good piece of code that was verified at one point, and that's it's not the result we sort of dream of, but it's a good result still.
Right.
If people want to give F-star a shot, where should they start?
fstarlang.org. There's we have an online tutorial. I actually just pushed a bunch of new chapters there last week. So there's I think what's up there right now, like if you wanted to learn how to write purely functional programs in F-star and prove them correct, I think there's a bunch of material up there that can help you get started. I think doing things that are, we also have tutorials up there that sort of help you write, say, C-like programs in F-star and prove them correct and get C code out of it in this subset of F-star that we call low star. But these things, I have to say, it gets substantially harder. Like if you're writing pure F-star programs, things can be kind of nice,
straightforward,
relatively, yeah, they can be, straightforward, or maybe even if not straightforward, it can be kind of pleasant and elegant, if you set it up right. But as you try to do fancier things with, efficient low-level code and proofs about them, things are still hard, I would say.
Sure. That seems to be the case with most languages that are a little bit on the cutting edge like that.
So relating to having it be a little harder to prove the sort of low-level imperative programs, one of the things we find in our tools a lot is one of the hardest parts of tool development is what you do when the person doing the proof is stuck. So when we talk about tutorials, it's kind of nice because you go through and there's the answer and it's going to work. Where we spend most of the time in our proofs is when it doesn't work and we have to figure out what to do next. Is that something you put some work into in F-star and making that story reasonable for your users?
Yeah, that's a great question. We put some thought into it, but there's so much more to do. And I mean, I think that's kind of the sort of the double-edged sword of having lots of SMT-based automation. You're trying to get this automated theorem prover to solve undecidable problems, and it's not. Sometimes it's just not going to do it. And then how do you, if a proof fails, how do you explain to a user why it failed and how to nudge the user from where they are towards a proof that may succeed? And I think F-star is not particularly good at this. I should be frank about it. Like we will try to get an error message out of the SMT solver and tell you, oh, we failed to prove this particular property about you, this conjunct in your formula that you tried to prove here. We were not able to prove it. And that's it. And, we don't, and sometimes if the SMT solver just times out, it may not even tell you why, which part of the formula it was working on when it timed out. And so sometimes we'll say, well, here's this chunk of code, we were trying to prove all these things in it, but we can't really zero in on like exactly which part of it failed. So I think this kind of diagnosis of proof failures it's a big thing that there's lots more that we should be doing here that we aren't. So usually this often involves like once you gain some experience with the tool, you kind of get a sense of like that the solver is and all the other things F-star is doing. It's not just the SMT solver. It's also how does the unifier work and how when is it going to be able to prove things by symbolic execution and things like this. You get a sense of like you have all these proof tools available to you, and you kind of know which work well in which situations. And when a proof fails, you say, all right, well, I know I'm trying to do a proof here about modular arithmetic, and I know the solver isn't great at doing, the SMT solver isn't great at doing that. So I'm going to, for this part of my proof, I'm going to resort to some other technique, maybe, use a library of lemmas that we have around that are going to tell you specific facts about modular arithmetic and do proofs that way. Or maybe at that point you realize that, hey, I should just abstract away a lot of these details. Like I'm not actually, I don't really care to be reasoning about, modular arithmetic in integers. I just care about, I can just work in some much more abstract setting and my proofs become simpler, and then I can just instantiate it to the specific setting I have in mind. So I think people learn, as in most tools, I guess, you learn sort of your way around, and how to how to navigate complex proofs.
Right. And the question, I think, is really how do we get the tools to provide a little more of that, rather than having humans need to rely on instinct so much. But that was definitely a tricky question, because I think in my opinion, no one's doing this very well. So I would have been really excited if you were like, yeah, we know the answer and you all can copy it, because I don't think we're doing great at it. I think people, I guess, are referring to some of these tools as sort of the autoactive verification tools, and I don't know if anybody in that space has a great answer to this question of like, how do we bridge the gap and like switch over from the SMT solver failing to the proof, the person doing the proof, like getting some useful information out of that and go back and forth in a good way. But it's definitely a really exciting question, I think, that a lot of people are struggling with right now.
Yeah, I think it's a really important question. It's also the sort of thing where the incentives in the academic community are not or at least in the core PL community, are maybe not structured well, that well for exploring these kinds of questions, because there's no clear answer. There's no theorem you can prove about this. It's you need usability studies and things like this. You try to extract as much information as you can from the solver and present it to the user in some useful way. Like, this problem is super underspecified, right? And you just have to, I think here's where you kind of have to sit in a very tight loop with your users and figure out if what you're doing is helping or not. But it's a really important space, and it's kind of wide open.
Cool. Well, I think we'll leave our listeners with that as a question to ponder, and to reach out when they have the tool that has solved this once and for all. But yeah, definitely how to get the incentives right is a challenge in this space, as well as the problem itself. But this has been a wonderful episode. Thanks so much for joining us, Nick.
Thank you.
Yeah, thanks, Joey. Thanks, Scott. Had a really good time too.
Glad to hear. This was another episode of Building Better Systems. Join us again next time.